So in the last class that we had, we were discussing the methods of finding the particular integral. So one method that we discussed in the last week was method of variation of parameters. So the basic concept is, if our complementary function is c1y1 plus c2y2, then we change the parameters c1 and c2 to functions of x, ux and vx. And our particular integral will be a function of, will be in this form, ux times y1 plus vx times y2. Now, how do we find? So, of course, this is restricted to equations of this type, y double dash plus p of x times y dash plus q of x times y is equal to capital X. And how did we find this ux and vx? Using this formula. Ux is minus of integral y2 by Wronskian times x, the right hand side of the differential equation, dx, and vx is y1 by Wronskian times x dx, and the Wronskian is determinant of y1, y2 and their derivatives, y1 dash, y2 dash, is the Wronskian. And so the particular integral is this. So we did an example on this. Okay, in fact, two examples on this problem. Now, the next method is that of the second method, which is very simple and much easier. Just that little logic we need to understand. After that, we'll be able to solve this. This is the method of undetermined coefficients. Method of undetermined coefficients. Now, very important to note. Now, this method of finding or solving for the particular integral is valid only for linear differential equations with constant coefficients. It is not valid for all types of linear differential equations. And only some standard specific functions x on the RHS. So this method of finding the particular integral is valid only for linear differential equation with constant coefficients and only for some standard specific functions x on the RHS. So the idea, the basic idea is this. Basic idea is choose the PI particular integral in the form similar to x, similar to the right hand side, and involving similar to x involving unknown coefficients, unknown coefficients to be determined by substituting uh, the pi in the given LDE. So we assume a pi to be in a form similar to the right hand side with some unknown coefficient, substitute it, and we can solve. So here is an important table. The RHS X and the choice for the particular integral. So if the RHS is in the form of k e power alpha x, then choice for the pi will be replace k with some unknown constant c e power alpha x. So generally the particular integral will be going by this form. Whatever is the form on the RHS, similar. So next, if it is k times x power n RHS, then the particular integral will be of the form a polynomial a power n x power n a n x n a n minus 1 x to the power n minus 1 a n minus 2 x to the power n minus 2 and a1 x plus a naught. So choice of this pi will be this one. Next, if the right hand side x is in the form k sine ax and k cos ax, then for both of these cases, the choice of the pi particular integral will be a1 sine ax plus a2 cos ax, because they are complementary functions, trigonometric complementary functions. So we have to choose it this way. Next, if is k e power alpha x and cos ax and k e power alpha x sine ax. So exponential and trigonometric combined. First one was exponential, second one was algebraic, then it was trigonometric. This is exponential and trigonometric as a combination. In this case, the particular integral will be of the form e power alpha x times a1 cos ax plus a2 sine ax. So in this form, we can choose. So these are the undetermined coefficients. So what is the method? Method of undetermined coefficients. What have we done? We have based on x, we choose a particular pi and then substitute that in the equation and we find the solution. Now, how to do this? What is the method? So rules for the method of undetermined coefficients. Now, this has three rules. First one is called as the basic rule. If x on the RHS of the LDE, the linear differential equation, is one of the functions in the first column of the above table, then choose the PI corresponding to it in the second table, in the second column. Then substitute in the LDE and evaluate the undetermined coefficients. Substitute the this PI in the LDE to obtain the unknown coefficients. Okay, so this is the basic rule. So this is the simplest form and there's no issue with this. This has slight modification for certain conditions. This is the basic rule which we'll do, but some modification. If now if a term in our choice of the PI happens to be a component of the complementary function. Complementary function is the solution that we obtain for the homogeneous part of the linear differential equation. So for the complementary function, then multiply the PI with x comma x square comma x cube or x power n okay, the lowest possible integral power of x which is large enough which is large enough which is large enough so that none of the terms of the complementary function match this term. So if complementary function has a component, then multiply it with x. If x into that function appears in the complementary function, then we have to choose x square into that function. So this is the basic. And then we have what we call as the sum rule. This is one if x is a sum of several functions in the first column, then first column of the table, of course, of the above given table, then the pi chosen should be the sum of functions corresponding to the second column. So corresponding to the first column, whatever is the second column. So if the sum involves the sum of two functions of in the first column, then the pi chosen will be sum of the corresponding functions in the second column. Okay, so now we'll do examples on this. So this is a very easy type of a method, which is logical, and we can very easily do this. So let us look at the first one, solve for pi. We are doing only pi, not the complementary function. Of course, we will have to evaluate complementary functions so that there are no issues. Which rule we are following, we have to be careful. So now look at this. This can be solved. So this is d square plus 4 times y. So 2 plus 2i and minus 2i are the coefficients, the powers, the solution of the auxiliary equation. And then to find pi, we know how to do this. We just use the binomial theorem. 1 by d square plus 4. We will use the binomial theorem and expand and do all that. That we have done already, how to find pi. Now, by the method of undetermined coefficients, using the method of undetermined coefficients. Eight x squared. So now d is plus or minus 2y. So of course, the complementary function is of the form, complementary function will be of this form, y is equal to a1 cos 2x plus a2 sine 2x times e power alpha. Alpha is 0, so we get this. So you don't have to worry on that. Now let us look at the right hand side. Right hand side is x power n, x square. So we have to choose such that a polynomial such that its highest power is x power n. So we go down. So here the right hand side is x square. So choose the pi as follows. The particular integral as follows. So we get a2 x square plus a1 x plus a naught. So we have chosen this. There are three undetermined coefficients now. And none of these components match with the complementary function. So you don't have to worry. So we have to apply the rule A. That means directly substitute this assumed pi into the equation. Now, since yp is the particular integral, it must satisfy the given differential equation, given linear differential equation. Therefore, so yp we know, yp dash is 2a2x plus a1, yp double dash is 2a2. So substituting in the LDE, y double dash plus 4y is equal to 8x squared. So we get yp double dash plus 4yp is equal to 8x square. This gives 2a2 plus 4 times a2x square plus a1x plus a naught is equal to 8x square. So now let us equate. So we get 4a2x square plus 4a1x plus 4a naught plus 2a2 is equal to 8x square. So comparing the coefficients on the left hand side and right hand side, comparing the coefficients. On both sides, we get 4a2 is equal to 8, which implies a2 is equal to 2. Next, 4a1 is equal to 0. Coefficient of x is 0, which means a1 is equal to 0. Next, we have 4a0 plus 2a2 is equal to 0, which implies 4a0 plus 2 into a2 is 4 is equal to 0, which means a0 is equal to minus 1. So we found a0, a1, a2. Therefore, yp is, this was our yp, a2x square. So a2 is 2x square plus 0x minus 1. So this we have found the particular integral. This is the particular integral. So a logical and a simple method to find by undetermined coefficients. Clear? So we assume the function, substitute, find the coefficients. So you found the pi. It is as easy. Don't even have to use the inverse differential operator, inverse operator. So next example, solve for pi for this differential equation y double dash minus 3y dash plus 2y is equal to e power x. Now, important, you have d square minus 3d plus 2 times y is equal to e power x. Auxiliary equation is d square minus 3d plus 2 equal to 0, which implies d minus 1 into d minus 2 is equal to 0, which implies d is equal to 1, comma 2. Therefore, the complementary function for the homogeneous part is y is equal to c1 e power m1x plus c2 e power m2x. Now, interestingly, this coincides with the x on the right hand side is of the same form as one of the components of the complementary function. So we have to use the modification rule. So same x, you just cannot write as cx. So use modification rule. So assume pi to be of the form what? E power x is right, constant is right. We multiply with x because we have e power x as the common. So we multiply it with x. So that is the modification rule, what we discussed here. If a term in our choice of the pi happens to be a component of the complementary function, then multiply the pi with x, x square, x cube, or x power n, the lowest possible integral power of x, which is large enough so that none of the terms of the complementary function match with this term. So that's the idea. So our choice of pi would have been c e power x, but that matches with the term of the complementary function. That is why we multiply with x. Now there is no match. So now what is the first derivative? C times x times e power x plus c e power x. So you have c into x plus 1 times e power x. Second derivative c into x plus 1 times e power x plus c times e power x, differentiating this. So we get c into x plus 2 e power x. So now the given differential equation yp satisfies the given differential equation. Therefore, what is the given differential equation? Y double dash minus 3y dash plus 2y is equal to e power x. Therefore, yp double dash minus 3yp dash plus 2yp is equal to e power x. So we have yp double dash is c into x plus 2 e power x minus 3 times yp c into x plus 1 e power x plus 2 yp c x e power x yp. This is equal to e power x. So let us see what should be c. Uh, collect x e power x terms. So c is common throughout, c times x e power x. So 1 minus 3 x e power x plus 2 x e power x. In constant terms, 2c minus 3c is minus c. 2c e power x minus 3c e power x, that is minus c e power x. So here this term automatically goes to 0 irrespective of c. So this term is 0. 1 minus 3 plus 2 is 0. Minus c e power x is equal to e power x. So this implies c is equal to minus 1. Therefore, yp, which is this, yp is this, cx e power x, c is minus 1, is minus x e power x. This is the answer. So this is how we solve for the um, particular integral in the linear differential equation with undetermined coefficients. One more. What if there is x e power x in the solution complementary function? Let us look at that. Another example, solve for the pi. Okay, solve for the complete solution. Both complementary function and the particular y double dash plus 2y dash plus y is equal to e power minus x. Y of 0 equal to minus 1 and y dash 0 equal to 1. This is the condition. So solution. First thing is to find the part 1 or step 1 of the solution. Finding the complementary function. So let us look at. So complementary function for the homogeneous part. So you have d square plus 2d plus 1 times y equal to 0. So auxiliary equation is d square plus 2d plus 1 equal to 0, which means d plus 1 the whole square equal to 0. So there is a repeated root. D is minus 1 and minus 1. Therefore, the complementary function will be of the form y. I'll write complementary c, yc is c1 plus c2x times e power minus x. because it's a double root, repeated root. C1 plus C2x into e power minus x. This is the complementary function. Now, the particular integral. Finding the particular integral. Of course, we can use that method of 1 by d minus d plus 1 the whole square on e power minus x, and we can do that. We can always solve by the operator method, but there's a easier method. So finding the pi. So now, interestingly, look at the RHS of the differential equation. It contains e power minus x. What is the complementary function? It contains e power minus x, and it also contains x e power minus x. So you have simply e power minus x and also x e power minus x. So e power minus x and x e power minus x are terms of the complementary function. Therefore, choose the complementary function to be of the form, sorry, not the complementary function, choose the particular integral to be of the form x square. So you have c x square e power minus x. Now, let us find out c first. So yp dash is c times x square into e power minus x derivative is e power minus x minus 1 plus 2x e power minus x. Okay. So you get c into minus x square plus 2x times e power minus x. Y double dash. C, now keep this as it is with a minus sign. Derivative of e power minus x is this, plus differentiate this 2x plus minus 2x plus 2 e power minus x. Okay, so simplification. We have x square term, and we have minus 2x, and minus 2x becomes minus 4x, and we have plus 2 times e power minus x. Now, substituting yp in the linear differential equation, we get, so yp double dash plus 2yp dash plus yp is equal to e power minus x. So use this. Yp double dash is c times x square minus 4x plus 2 times e power minus x plus 2 times yp dash is c times minus x square plus 2x plus, what is yp? C x square e power minus x is equal to e power minus x. So let us collect the terms of x square, c times x square e power minus x terms. So you have coefficient 1, then you have minus 2. See, if you take out minus 2x square, so minus 2, and then plus 1. So that will go anyway. Then we have x terms. Let us see the x terms. C times minus 4 plus 4 x e power minus x. This also cancels. Then last we have constant c times 2 plus 1 x square. No, I'm sorry. This x square, this x. So only we have, this is not that. We just have 2c e power minus x. 2c e power minus x is equal to e power minus x. So this is 0, this is 0. So no issues about that. So we get c is equal to half. So what is yp? Half of x square e power minus x. Therefore yp half x square e power minus x. Therefore the total solution, the complementary function plus the particular integral. Now the complementary function we found here was c1 plus c2 x e power minus x. So c1 plus c2 x times e power minus x plus half x square e power minus x. Now we have to apply the boundary conditions given. Y naught is y of 0 is minus 1 and y dash 0 is equal to 1. So y is given to us here. So y dash, the derivative of y is, differentiate this, c1 plus c2x into e power minus x with a minus sign plus, differentiating, keeping e power minus x, differentiating this, we get c2 times e power minus x plus, differentiating this, half into 2x e power minus x plus x square into minus e power minus x. So this implies y dash. So we'll simplify the terms, of course. Okay, I'll just leave it here. When we substitute y of 0, it will make sense. So two conditions. Y of 0 is equal to minus 1. This will imply, substitute x equal to 0. Here, so substitute x equal to 0. So y of 0 equal to minus 1 means minus 1 is equal to c1 plus 0 times e power 0, that is 1, plus half 0 e power 0. So this, we are left with C1, which implies C1 is equal to -1. Now y dash 0 is equal to 1. This implies, substitute 0 here. So we have -1 on the, sorry, +1 on the left hand side here in this equation. Now substitute, this is C1 plus 0 e power 0 plus C2 e power 0. And these terms are 0. Half times 0 plus 0, because x is 0. You don't have to worry. Now, this is 1. This is minus of -1 C1 plus C2, which gives that C2 is equal to 0. We get C2 is equal to 0. Therefore, C1 is -1. So in this total solution, we found that C1 is -1 and C2 is 0. Therefore, the solution to the differential equation is y is equal to C1 is -1 times e power -x. So C2 is 0, -1 plus half x square e power -x. So this is the solution. So this is the method of, undetermined coefficients. So this is a simple method. Method of undetermined coefficients. Next. The next type of equation, a very, very important equation from gate or gate point of view. More than the variation of parameters and undetermined coefficients, they may ask conceptually, but this they ask. So Euler-Cauchy equation. Euler-Cauchy equation. Now this Euler-Cauchy equation is an homogeneous equation, is a homogeneous equation of the form x square y double dash plus ax y dash plus by equal to 0. So look at the coefficients. The coefficients are with the double dash, there's a square term x raised to power 2. With single derivative, there is a linear term x, and with the function as it is, there is no term. So this type of equation is called as the Euler-Cauchy equation. So now it's a homogeneous equation. So the solution for this, it's a standard one, the solution is of the form, the solution is of the form y is equal to x power m. Now we can have coefficients, but even if you have coefficients, the coefficient comes out common, so it doesn't matter. Because it's a homogeneous equation, coefficient will not matter. So straight away, you can choose x power m. Now, by substituting, we get x square into m into m minus 1 x power m minus 2. This is the second derivative, plus a into x times the first derivative m x to the power m minus 1 plus b x to the power m. So you get m into m minus 1 x to the power m plus a into m x to the power m plus b x to the power m is equal to 0. So we get m square minus m. We are taking x power m common, plus am. So we get plus a minus 1 times m plus b x power m is equal to 0. So x cannot be 0. So x power m cannot be 0. So what the solution comes from this equation. So this is called as the auxiliary equation for the Euler-Cauchy's equation. So for linear LD with constant coefficients, it was different. So for Euler-Cauchy equation, the auxiliary equation is this: m square plus a minus 1 times m plus b equal to 0. So now it has uh, roots, real distinct, two roots, real distinct or real equal or complex. So case 1 for auxiliary equation. So case 1, when auxiliary equation has two real and distinct roots. Then the general solution is of the form, the general solution is of the form y is equal to c1 x to the power m1 plus c2 x to the power m2. So x power m is the function, right? This is the assumed function. Solution is of this form. Now, this is the general solution. Two real and distinct roots, m1 and m2. So we get this. So this is the general solution. Case 2, double root. M1 is equal to M2 is equal to M. M1 is equal to M2 is equal to M. So then what happens is like this. So if it has a double root, the discriminant is equal to 0. B square minus 4b equal to 0. So we get b is equal to a minus 1 upon 2 the whole square. B should be like that from this. Then this condition comes. Now the solution is like this. General solution or the is of the form y is equal to c1 plus c2 log x times x power m, where m is equate m will be minus b by 2, that is minus of 1 minus a by 2. So where m is 1 minus a upon 2. The solution, if roots are equal, so discriminant is 0 and m will be minus of b plus or minus under root of the discriminant by 2. So m is sorry, this a minus 1. So this is 1 minus a upon 2. 1 minus a upon 2. So this is the solution. So here, remember, when we choose e power x, then when there was a double root, we chose c1 plus c2x e power x. Here you will get log x because derivative of log x is 1 upon x. So it merges with this term. So here for double root, you have to write c1 plus c2 into log x. You can show this. We are skipping all that detailed proof, but we can show this. Now case 3, complex roots. M1 is equal to alpha plus I beta and M2 is equal to alpha minus I beta. So the general solution here is of the form y is equal to e power alpha x. Yeah, sorry, it's not e power, it is x power. We are dealing with x power m. So x power alpha into x power I beta into x power minus I beta. That's what we get. So x power alpha times we get a1 or a cos of beta log x plus b sine of beta log x. So these three cases are very important for complex roots, for real and equal roots, and for real and unequal roots, real and distinct roots. This is the complementary solution. This is how we solve for the Euler-Cauchy equation. So let us take examples, easy ones. Solve x square y double dash minus 2.5x y dash minus 2y equal to 0. So this is clearly an Euler-Cauchy equation. This is Euler-Cauchy equation. So let y be equal to x power m. So we get directly, if we remember, it is all right, or we need to write this m into m minus 1 into x power m minus 2 minus 2.5 x times m into x to the power m minus 1 minus 2 x power m is equal to 0. We are substituting. So x power m comes out throughout. We have m square minus m and minus 2.5 m minus 2. So m square minus 3.5 m minus 2 equal to 0. So let us see this 3.5 multiplied throughout by 2, 2m square minus 7m minus 4. So 4 to 8. So 2m square minus 8m plus m minus 4 equal to 0. So we get 2m plus 1 into m minus 4 equal to 0. So solution is m is equal to minus half comma 4. Therefore, the solution, the general solution is y is equal to c1x power m1 plus c2x power m2. So y is c1 x to the power minus half. So 1 upon root x plus c2 x to the power 4. This is the solution. This is the general solution of the Cauchy's equation, Euler-Cauchy's equation. Let us look at the second example. Solve x square y double dash minus 3x y dash plus 4y equal to 0. So let y be of this form, x power m. Then x square into m minus 1 times x power m minus 2 minus 3x into m x to the power m minus 1 plus 4x to the power m equal to 0. So we get m square minus m. Then we have minus 3m plus 4 equal to 0. So we have m square minus 4m plus 4 equal to 0. So we have m minus 2 the whole square equal to 0. So we have m is equal to 2 comma 2, a repeated root. So we have got a repeated root. So solution is of the form y is equal to c1 plus c2 log x times x power m. This is the, because it is a double root, repeated root. c1 plus c2 log x. Very, very simple. Should not miss a problem on this. Next, example 3. Solve x square y double dash plus 7x y dash plus 13y is equal to 0. So solution. So again, y is of the form x power m. This gives x square into m minus 1 x to the power m minus 2 plus 7x into m into x power minus 1 plus 13x power m is equal to 0. So take out x power m terms throughout, and we have m square minus m plus 7m plus 13 equal to 0. So we have m square plus 6m plus 13 equal to 0. Now m, discriminant b square minus 4ac, 36 minus 4 into 13 is negative. So minus b plus or minus root of b square 13 fours 52. So 36 16. So minus 6 plus or minus 4i by 2. So minus 3 plus or minus 2i. Therefore, the general solution is of the form x to the power alpha, so x to the power minus 3 times c1 cos beta is 2 log x plus c2 sine 2 log x. This is the solution. So all three cases, one example. How to do? So this is the Euler-Cauchy equation. So what did we discuss today? We discussed the method of undetermined coefficients and Euler-Cauchy's equation. Both of them are quite simple and straightforward. With this, we complete the discussion on the linear the ordinary differential equations by the standard methods. Now we go for Laplace transform. Laplace transforms is one of the transform methods to solve the differential equations. So that is a chapter by itself. Once we complete Laplace transform, then we go for Fourier series and Fourier transform and partial differential equations. And once that is done, we are left with probability statistics. So that's the main topic. Other topics are all small. So now we'll have a break because I'm taking an extended class. So after half an hour, we will again join back. Okay. Thank you. I'm giving a break for half an hour.